Hello and welcome to the Miko Bits show, and I'm your host, Miko Bits. Today we have Ismael from Lagrange, and he's working on a very, very important piece of mathematics, which is cryptographic proofs. So really, cryptographic proofs are the mathematics of deterministically knowing something and being able to demonstrate that it's factually correct, right? So I think that's a very important field. And I think to me, it'd be great to kind of zoom in and welcome Ismael to the show, talk a little bit about kind of, first of all, why proofs. So welcome to the show.
Thank you for having me, Nico. Excited to be on. And I think that
Yeah,
lead-in
wonderful.
is very apt,
Yes.
especially with the mathematics and the applied cryptography that we focus on. Very much so, it's about being able to prove and to verify underlying properties of information that would otherwise be trust-based in their consumption.
Yeah, I think this is so important for the audience to understand, right? Which is
Mhm.
that I think one of the things that's so critical as we go forward, right, is everybody has seen crypto scams, right? So they've seen things where people have been defrauded, right? And so, so people are now in this weird mood where, so the word crypto has really come to mean cryptocurrency, right? But the underlying reality is that you and I want to talk today about cryptography, which is another crypto, right? And
It is.
cryptography is not about, cryptography is about mathematical proofs that things are true, right? So in a
Mhm.
sense, cryptography isn't the problem. Cryptography is the solution, right? So what I'd love to do is kind of have you comment a little bit about sort of like, cryptography and kind of how you see sort of the state of the internet.
That's very true, Miko. And moreover, crypto or cryptography is the original crypto.
Yes.
Cryptocurrency is an embodiment of technology that leverages cryptography, but is not the totality of what is cryptography. Cryptography is the foundation of what secures the internet today. And as the internet changes, it will continue to be the foundation of what secures it going forward. All the way from network routing now to being able to verify information in an increasingly hard to verify world. Cryptography serves as a foundation. And so when we look at the internet today and we look at the advancements of AI and the advancements of adjacent technologies, it becomes harder and harder to ascertain whether or not the information we are consuming is true. Is this a deep fake?
Hi, everyone.
Is a foundational component of ensuring that the people you're interacting with, the information you're seeing, all of that is in fact what you believe it is.
Yeah. What I love about this is, my ethos is really about open source
Mhm.
financial infrastructure, making the world more inclusive and fair and just and transparent and innovative, right? So in looking at these characteristics, like cryptography becomes so core because the idea of having mathematical proofs really then allows people to conduct commerce or conduct any kinds of activities, financial trading, whatever the kind of economic activity they want in an atmosphere where they can actually rely on facts, right? And
Mhm.
to me, the thing that I think is exciting that we're witnessing, and perhaps very bad actually, is the collapse of Web 2. Right. So, we're seeing obviously Twitter is filled with bots. The Jack Dorsey that doesn't want to run a company called Twitter, and Mark Zuckerberg doesn't want to run a company called Facebook, right? They want to run companies called Block and Meta, right? So like
Mhm.
I think even the founders of Web 2 have acknowledged that it's basically over,
Mhm.
and that it's going to get worse, right? I think AI is going to completely destroy
Mhm.
the fabric of what we consider to be online reality, right? Deep fakes, like, bots, botnets, like fake
Mhm.
users, fake content, fake everything, right? So to me, like, if you look at a world that's already fake, like Instagram,
Mhm.
like it's gonna just end, right? Because
Mhm.
it's sort of like, well, my fake life generated by an AI is gonna look even cooler than your fake life that you generated through like
Exactly.
falsifying, your friends or whatever, right? So like the whole concept of having a fake life is gonna be of very little value because the ability to generate, the cost of generating a fake life is gonna drop to close to, very, very cheap. It's gonna be very cheap.
It's very true. And I would say that the beauty of it is talking about financial infrastructure and the tools that underpin secure decentralized financial infrastructure now becoming extensible and continuing to secure other aspects of life really is a natural progression when you think about it. If you think about the core of cryptocurrency, of Bitcoin, it's really to allow a trustless peer-to-peer transfer of a piece of data, state. I have a Bitcoin that I want to transfer to Miko, and I don't have to. Miko doesn't have to trust me. He can just trust that the underlying protocol ensures that I have a Bitcoin or the divisible amount of Bitcoin that I want to transfer to him. And as we think about the extension of that, to Miko's point, there is going to be the ability to leverage the same underlying infrastructure to prove other properties of information, the provenance of your life, the provenance of your identity, the provenance of your experiences and the photos of your reality.
Yeah, I think that that's going to be very exciting, right? And I think that, to me, we've moved from the Bitcoin era, which is the era of trustlessness, right? Which is obviously the thing that is sort of like completely on-chain everything, right? To the era of kind of trust minimization, right? Which is kind of like this idea of proving certain elements, right? Like, so I think that's kind of the exciting part, right? Because one of the things that you're working on are things like cross-chain proofs,
Exactly.
right? And cross-chain proofs are really related to the field of trust minimization, right? Because what you have is you have one mathematical realm and you have a separate mathematical realm, right? And you need to be able to connect them or bridge them, right? So obviously, you can create a mathematical proofs, but it's ultimately, each realm is sort of subject to its own math, right? So I guess I'm really wondering kind of how your views are on cross-chain proofs, versus kind of other kinds of proofs.
That's a very good question, a very good point. The way I like to think about it is that you have these incredibly powerful underlying state machines that allow you to conduct financial transactions and to build applications with increasing levels of technical complexity, all the way from exchanges for money to lending platforms. But when they're on different blockchains, they're fundamentally separate in the data they have access to. And what we focus on is very much that data, that state problem. How do you allow these different ecosystems that have these different underlying applications to be able to communicate and securely transfer information between each other in a capacity that does not subject the average user to a poor experience or risk an insecure movement of their assets?
Yes, I one of the jokes I've been playing with lately is I don't know if you've seen the meme of like the average guy and
Yeah.
then there's the really dumb guy and then there's the super genius, right? So my concept is this, right? Which is that the average guy in crypto is shouting something like, "We have to separate money from the state." Right,
Exactly.
that's the average guy, right? The dumb guy is basically in living in a fiat world. So the dumb guy is the money is the state, right? That's what they think, right? That's the world of fiat money, right? That's the dumb guy. But the super smart guy is saying money is just on-chain state.
It is.
So that's my joke. Is like it's sort of the bell curve between the dummies and the smarties, right? So the dummies and the smarties both think that money is state. It's just that the smarties define state as being a sort of a completely different construct, right? So anyhow,
Yes.
what I'd love to delve into is sort of like tell me a little bit about sort of Lagrange. Tell me a bit about kind of like, for example, like the world of like a zero knowledge proof. So I'd love to kind of have you unpack that a little bit for
Yeah.
my audience.
I think that's a very good point, and I love the concept of state being a dual meaninged word, both in terms of what we would conceptualize as a state of a nation state, as well as the state of a decentralized and underlying ledger of information, where
Yes.
functionally, to your point, all data on a blockchain, whether that be account balances, asset holdings, the information on the underlying financial products you interact with is all data, is all state as well.
Yep.
And what we focus on is building tools to increase two things: the security of how you work with that state, as well as the expressivity, the types of things you can do with that data that permeate into ensuring that applications that build on blockchains have these robust and data-rich features that they would otherwise be able to leverage in Web 2. And so that's sort of how we frame the problem space and the industry that we work in. And we have very specific products that are highly technical that are oriented toward each of those, but at a high level, that's how we think of it.
I like that. I think one of the really funny things when you actually start to think about sort of the gigabrain side of the concept of state, right, which is really related to statefulness, right, which is really kind of like servers and this kind of mindset, right? But like when you go all the way to Balaji Srinivasan and you go to the network state, right? The thing that's really funny is that when you think about the network state, the ledger of the network state that kind of governs the balance sheet of the essentially central bank, the decentralized central bank of any network state, right? The thing that becomes really funny is that if someone hacks a bridge, it's basically a coup d'etat, right? It's basically a blow to the state, right? That the state itself has been, right? So in a sense, the concept of the state being a state, right, is actually a pretty interesting digital construct, right? But playing with this though, right? Then if you really reason about this future, the thing that I think is really vitally important is that, you know, everybody does talk about this kind of future idea of the value of the digital commons and the value of this kind of network community, right? But obviously, as AIs increasingly degrade our confidence in the information that's flowing across Web 2, you know, I think that we're increasingly reliant on these wonderful mathematical proofs, right? So I guess the thing that I'm kind of curious to get from you is sort of like, how do you see sort of the steady state or the future of kind of the internet, right? The future of the internet from the perspective of like proof and from the perspective of cryptography.
That's a very good question, and one that might take longer than this show to unpack. But what I can say is the way we think about zero knowledge proofs is as a way to compact a large amount of computation into an easily verifiable proof. So you could run an arbitrary amount of computation ranging from anything to processing large amounts of data to running even a traditional application you'd run on a Web 2 server, all the way to machine learning in a computational and mathematical substrate that allows you to verify the result of that with far less computational requirements to verify than it would otherwise cost to compute. And so to put that kind of abstract concept into practice, it means you can start using the underlying security of blockchains to secure things that are beyond what can actually run on that blockchain. So for instance, applications that have large computational requirements can write proofs to the blockchain that would otherwise, if when executed everything natively on the blockchain, be too computationally expensive.
That definitely makes sense to me. I think that the cost factor is super interesting, right? There, to me, the thing that I think is so interesting is you're talking about the cost of verification, right? And I think that that becomes such a cool concept, right? Because if you go all the way back to there's actually a wonderful Islamic proverb that says, "Trust in Allah, but tie your camel." Right. So so the idea behind that is this concept or paradigm of trust, but verify.
Yes.
Right. So the question then becomes, how can we have a valid state of the internet where such verification becomes sort of a standard part of interacting, right? And to me, the thing that becomes really interesting as you start to kind of explore and develop R&D is that what you're talking about is you're talking about the cost of verification, right? Because if the cost of verification is huge, then it's just not going to make sense for us to do it. Like it's just going to be like, wow, you know, because so for example, if you have a huge computation and the cost to verify the computation is to run the huge computation again, right? That's kind of prohibitive and it probably won't happen, right? So I think what you're talking about is you're talking about taking very complex computation and basically coming up with extremely low cost ways to just check, right? Because if you can make if you can make checking super fast, and if you can make checking super cheap, then it makes economic sense to check everything, right? Like you might as well.
Exactly.
Doesn't cost much. Let's check everything, right? So if you're checking everything, then you're gonna be safer, right? Like your
Yeah.
whole internet world is going to be, it's just going to be a better internet world because
Yeah.
things will be verified, right? You won't have to kind of have that feeling of like, fear basically, because, at the moment things on the internet seem to be eroding and degrading in front of our eyes. I think deep fake technology is coming, like I think the amount of fakeness is going to exponentially expand. So, I think verification becomes super big. So tell me a little bit about kind of how do you reduce the time and size and cost of verification?
Yeah, I think that's a very good question. And I think the question of verification versus execution is a very big one. The idea of execution would mean that we would take a large number of different centralized parties and have those independently execute something on our behalf, have them concur on a result, and then use that collective concurrence as the next canonical state of the world.
Yeah.
Verification is different. Verification is you can have any party execute something and then produce a proof of that, where now all of these parties can verify that execution without having to independently run that thing. And when you think about the internet broadly as a concept, it's all programmatic, all the way from the network layer to the application layer to the user experience layer. But that is a large stack of technology that is computationally far more intensive than what we could all independently run and concur on. If every time I made an API request or a computer request, I had to have Nico do the same thing and have 1,000 people do the same thing and have incredible computational burden would now be imposed on everything, right? I mean, you
Yeah.
can talk about
Yeah.
these incredibly large language models. If we had to run those 1,000 times, 10,000 times, and all agree on the result of it for a single prompt, it would be infeasible. Now,
Yes.
though, when you can have it run once, that computes a proof, and you can check that proof across a large group of actors with a high economic security behind that environment where the proof is checked, then you can start having trust in the execution of something by only having direct verification in a decentralized manner. And that's kind of the big unlock that you get with zero knowledge and with verifiable computation as a field.
So I'm going to ask a follow-up question, but what
Mhm.
I really wanted to do is clarify a little bit from sort of an audience perspective.
Mhm.
Like one of the really interesting things that you're describing when you describe something where a computation has to be run in parallel by many, many actors is you're basically describing consensus, right? So you're
You are.
basically describing why a smart contract on a layer one, like in Ethereum, is very expensive, right? It's
Exactly.
expensive computationally because you have so many nodes basically running the same exact thing. And it's sort of like, wow, that's a lot of effort, right? Everyone's
Exactly.
got their pocket calculator out. And in a way, it's redundant effort because everyone's doing the exact same thing, right? Which
Mhm.
is and obviously, if anyone does something that looks even slightly different from everyone else, obviously in the Ethereum system today, like they get slashed, right? They're basically like, wow, you're a cheating scumbag. And then they like take that guy's money, right? But like the thing that I wanted to talk to you about is like one of the things this makes me think about when you talk about this kind of concept of compression. It's effectively a bit like a non-lossy data compression construct, right? Because in a sense, like when you look at data compression, you're basically thinking of how can I take a large amount of information and then make it into a smaller amount of information that on the other side, the other person can unpack basically into the full amount of information, right? So in a sense, there's sort of
Mhm.
themes of mathematics that relate to the mathematics of data compression that kind of maybe relates to how you can create lightweight or compact proofs.
Yeah, I would say even kind of as an extension of that, what you're capable of doing is to take a large amount of computation and prove that. So rather than taking a large amount of data and compacting it, you're taking a large amount of computation and verifying it in a very finite computational environment in a way that confers the same security as if that large amount of computation was run in duplicate. And
That's
that's
super
a very
amazing.
powerful primitive.
That's super amazing. One of the things I'm really curious about are things like programmatic loops
Mhm.
and things because I feel like something like a loop is potentially pretty hard to deal with because in a sense the things that happen within computational loops is you can get things like infinite loops and you get into these things like the Turing halting problem, where you get into things where it sort of becomes conceptually even harder and harder to
Mhm.
make a compact proof of a program because as you get more and more sophistication in different types of programmatic constructs like loops, right, you get more and more exponential complexity in trying to like compress that or to reduce that into a proof, right? Isn't
Yeah.
isn't that sort of part of the problem set?
So I think it's adjacent to the problem set. So loops are a very interesting concept, right? Because you're running something that has to execute over all of the elements of a predefined setter list.
Yeah.
Where that becomes difficult is when you're talking about in two places, on chain, where you have to have duplicate execution of that because they become expensive. Because as the list
Yeah.
gets larger and larger, so does the cost to run across every
Yep.
element of it.
Exactly.
In
Yep.
circuits, you have to generate a proof across every element of that list, or you have to generate a proof that enumerates and executes something across every element of that list. And where that
Yeah.
gets difficult is that if the list size changes, so does the number of constraints in the circuit. And so does the
Totally.
circuit, which makes it hard to
Totally.
verify. Because if you had a circuit that had 10, 10 elements in the list and 11, or a
Yep.
circuit with 11 elements in the list, those would be two very different executions and would need two very different
Yes.
verifiers.
Yep. Gets very bloody, doesn't it?
It does. Dynamic data doesn't play well often with many proving systems.
So tell me a bit about the term circuit. So like how would you help people understand what that means? Because
Yeah,
it's frequently used in the ZK world.
yeah. I would think of it as a mathematical representation of the execution of a program that allows you to very easily verify the result of that execution, wherein you could pass
Nice.
the input to the execution, mathematical a mathematical proof that allows you to verify that with respect to a given input and a predefined computation, this is the output.
So tell me about the techniques that are used to make that cheaper and cheaper, right? Because it feels
Mhm.
like that's part of the magic mathematics that's currently kind of being applied
Yeah.
hammer and tongs, right? Because I think that there's sort of this dream of taking effectively almost all compute statements, in Turing compute land and basically reducing them to really low cost, very simple
Mhm.
proofs, right? Clearly there's some expressions that are harder than others,
Mhm.
right? And so there must be lots of techniques that are being sort of like applied to make this digestible problem.
There are. And what I would say is the ones that we're, in fact, the most passionate about are things that have to do with recursion or folding of proofs. In particular, when we think about having these very large computational constructions, running operations that require a large amount of compute can be made a lot faster if you're able to fragment that compute across a lot of machines. We talked about loops earlier, right? If you're, let's say, averaging everything in a loop, right? You want to add them all up and then divide them. You could, in theory, run that in one long execution where you go through everything and you add them all up, and at the end of the addition, you divide them. Or you could go in parallel and you could add the elements pairwise all the way to get to the end and then divide it. And in that case, the only time that this would take to compute would be however long it took to compute the first addition, and then log n times however long it takes to compose, where n is the width of the data. And so you
Yeah.
can start taking these very large constructions and you can start parallelizing how they're processed. So that you can process pieces of them on different machines and then add
Yeah.
them all up as you go. This is distributed
Ah,
computation, parallelizable computation, and a very powerful primitive that's beginning to be applied more commonly in how proofs are being designed.
that's kind of exciting to hear about because one of the really interesting microprocessor optimizations that I was
Mhm.
hearing about in talking with people who do circuit design at the hardware level is that there's actually a really cool optimization technique where if the software has an if statement, it turns out that there are ways in which the processor can actually run ahead and compute both branches of the if. So they can basically run ahead and compute if it's true, and they can run ahead and compute if it's false, right? And then basically what will happen when it's determined is that the pre-computed block will actually just immediately jump to the conclusion, right?
Yeah.
So it's very, very amazing how much you can get if you're willing to push into parallelism, right?
Yes.
Because that's only interesting if you have parallelism, right? Like if you have a single threaded, right, and you don't have any parallelism, then that optimization doesn't make sense, right? It's basically like, why are we're doing twice as much work and we're actually throwing away one entire branch of work. And it's like, why are we doing that? And it's kind of like, well, it turns out that Moore's law has kind of started to make parallelism really cheap. And it's starting to make kind of other things quite expensive, right?
Exactly.
So it feels like this kind of like idea that you can really lean into parallelism and that you can do really, really kind of, it's really interesting because it changes the dynamics of how you think about what's cheap and what's expensive, right? So
Exactly.
duplication isn't that expensive as long as you leverage parallelism, right?
Exactly.
So that's super cool. It's a very interesting observation.
It's very fascinating because as you start parallelizing stuff, you start running into traditional Web 2 problems in the assembly of proofs. If you were to maximize your parallelization, you're likely going to have, and with fast recursion time of these proofs and fast composition of them, what you're going to find is that the network communication overhead is going to start becoming higher than the actual proof composition overhead. So you start converging back to a Web 2 problem space if you're able to solve with increasing confidence some of the existing problems with how proofs can be composed and how proofs can be verified in a compact fashion.
Yeah, I think if you reduce it into human terms, right, the question is it going to take more effort for me to explain this to someone else and have them do it? Or is it going to take more effort for me just to do it, right? So in a way, if you look at it from a machine perspective, it's sort of compute bound versus IO bound, right? So IO bound basically means like you have to push it to someone else. And then obviously being compute bound is basically like, no, I'm just going to like do it here, right? So the question becomes the tension between those. The other thing that I'm seeing that's really exciting about the emergence of the CK space is that there's already lots of beautiful dialogue happening with compute optimization. So like obviously it's premature, but we're seeing folks like Cizik, we're seeing folks like Gingo Yama, we're definitely seeing the FPGA folks jumping in, right? So the thing that's really interesting is that there's kind of almost a crawling forward together vibe of like, of course we're going to get massive parallelization. Of course we're going to get vector computation. Of course we're going, so like people are basically feeling out this kind of coevolution of the way it makes sense to optimize based on assumptions about what the future compute state will be, right? So I like to see this sort of mental coevolution because I do think that, the future of the internet is definitely going to be, I would say, customized compute or maybe ASIC compute, but it's definitely going to be specialized compute.
It will be. It will be. And the very interesting part of it about it as well, this is one of the things we focus on, is being able to look at data sets as you would in Web 2 in a big data scale within verified computation in a zero knowledge context. Because what you're talking about is inherently parallelized compute that's run in Web 2. That's the foundation of how data is ingested from machine learning models, is the foundation of data is processed at scale. And to be able to take that parallelizable computation and prove that in further parallelization. And so you're parallelizing proofs of parallel.
Yeah, one of the beautiful things about the reduction in the cost of parallelism, right, is we're starting to see, like, if you look at something like, like CUDA and kind of NVIDIA and graphics processing, right? Like that's hyper parallel stuff, right? Like it's super vector computing, right? So what's happening is that there's sort of a cheapening of parallelization, which kind of makes this sort of verification world more practical, right? Because in a sense, like if you get parallelism super cheaply, then that you get kind of this wonderful world where like it's not that we're not fully replicating compute like we are in like smart contracts, but we're actually doing lots of parallel verification, right? Which is kind of like the thing that I think is amazing is that people are confused about what's expensive. Right. So in other words, if people are like, well, why are you doing any computation? Right. Like you're over there doing your verification. And it's like, why would you even bother? Right. And to me, the thing that people don't understand is what's expensive is lack of trust. That's what's expensive, right? People are mad at Bitcoin because they're like, oh, you're burning electricity, right? But it's sort of like the reason they're burning electricity is that the assumption of any given Bitcoin node is that it can't trust any other Bitcoin node and it can't trust any Bitcoin message, right? So if you start from that assumption, of course you're going to burn electricity. Like you have to burn something, right? So I guess what I'm trying to say is that when we start to move towards an optimal internet network architecture, right, I think that we've moved from the world of Web 2, which is let's just trust whoever it is and assume everything they're saying is true, which is proven to be a disastrous thing to do, to Bitcoin, where it's like, let's not trust anyone and let's do every single compute completely from top to bottom, and now we're moving into a much more, I think, beautiful state, right? We're moving into a beautiful state where it's kind of like, let's not recompute every freaking thing. But let's not check everything as a matter of policy either, right? Like let's try to find the mathematically smartest way to run the internet. That seems like a really interesting, a steady state and final destination.
I love that framing because the lack of trust is expensive. The creation of trust is also what's expensive. Because with a lack of trust in an individual node, the creation of trust around a collective body of nodes is what costs something. And so I think you have to ask yourself, in terms of proofs, what do I have to create trust around? And what is the pricing power on creating that trust?
Yep. 100% love that. And to me, the thing that's really interesting is that if you can lower the cost of verification, right, then what you're doing is you're basically competing with the cost of just blind trust, right? And the thing that's really funny about the cost of blind trust is the cost of blind trust is zero cost per transaction, but you have to amortize the cost of when the guy scams you and completely wipes you out, right?
Exactly.
And so if you amortize the cost per transaction, it's pretty horrible, right? So for example, if you're a user of FTX, right, and you have like 100 Bitcoins in FTX, the cost per transaction on FTX is like free, right? It's like free transactions. It's so great, right? I love this. It's a miracle. But it's like, oh no, but now all your Bitcoins are gone, right? So now you have to basically amortize the cost of like all your Bitcoins. And you basically realize like, this is way more expensive than I would have if I had a like hardware wallet and I had kind of done all the DeFi transactions, which of course you would have been angry at the time because you would have been like, oh my God, that transaction cost me like $30, so you'd be mad, right? But like in a way, the question becomes like, what's the optimal cost, right? And so the thing that I think is beautiful about where we're going in a network state is that we're starting to come up with agreements, right? We're starting to come up with agreements. So the agreement can be like, well, this is like a super trusty thing. So if you want like complete trustlessness, use Bitcoin. Like, go ahead. That's fine, right? But if you're kind of willing to take some amount of risk, then like maybe you should use like an L2 and that's fine. Maybe you should do optimism, right? Like, so to me, like this idea of negotiated trust levels is something that just shows advancement and sophistication and rationality. So I don't know. I'm just really excited about where we're going and, how much better it will all be.
I agree. And I would say to kind of loop back to one of the things we started with, when we think about cryptocurrency today, we think about the usage of these mechanisms to create trust in untrusted actors or across untrusted actors as a way to secure financial obligations. But as we think about this new internet and we think about the data that's required to process, to trust, ranging from, of course, financial, all the way to social, to news, et cetera, to the result of machine learning models, you are required to now create trust in new things that aren't as easy to settle as a simple accounting between two parties. And that's where machine learning that allows larger scale computation to inherit trust of where it's verified are becoming increasingly prominent.
Yeah, that's quite exciting actually, right? Because obviously to me the thing that happens is that trust kind of starts stacking up on top of trust, because in a sense like what you're building is you're building pyramids or you're building structures, right? You're building foundations, right? So in a sense if you have a base of trust you can kind of build higher, right? So
Hmm.
I guess the way that I'm kind of thinking about what you've just said, right, is that like we really need to kind of build more like a web of trust, and we really need to build a network that has that kind of trust inheritance pattern that you're describing, right? But
Exactly.
ultimately I think the final destination is really going to be, because here's the great thing, right, which is if you go back to the philosopher Plato, right? He talked about things like the world of ideals, right? So he's really talking about things like the Platonic solids, and he's talking about mathematics, he's talking about geometry, and he's talking about logic and order, right? And one of the great things that Plato never got to play with is digital computing, right? But to me, digital computing is as close as humanity has ever got to this perfect world of order and lawfulness and mathematics, right? And so to me, the thing that becomes really, really great is like, can we build a society that has the properties of transparency, of orderliness, of fairness, of determinism, of rules, right? I'm not a code is law person, but I do think that we can build a world that's more fair and more kind of trustworthy, right? And I just think so far we've been in a mood of like wild experimentation, and we've definitely had our share of like failures within the cryptocurrency industry, but I think that really in this build out of this kind of mathematically and platonically more ideal world, it does feel like mathematical proofs, and verification, and obviously this kind of diligent effort to reduce the cost of verification is going to really deliver a lot of fruit, and it's really going to enable us to be kind of living much safer, much more orderly existences on the network.
It
So
will.
I think that's my feeling. Any closing thoughts around the future of ZK, the future of what you're working on? Any promising avenues or things that you're excited about?
Yeah, we're very excited. We're going to be doing a testnet launch this summer for a big portion of our infrastructure around the trust and building trustlessness around cross-chain state. And we'll be doing another launch likely in early fall associated with the second part of our technology around trustlessly processing large amounts of data and large amounts of computation on data. And we think that these are going to be big unlocks for a lot of use cases in crypto and in the broader, I would say, new internet that require information and data in increasingly large quantities with increasing security.
Yeah, and I think that the last kind of like thing that I wanted to toss into the ring too, right, is that as people describe, so we did have a interesting show with Elena from Ironfish,
Hmm.
and she's sort of a privacy maximalist, right? So,
Hmm.
in a sense, the thing that I think is one of the offshoots of the style of trust development, right, is that if you have 100% verifiability of counterparty, if you can really understand kind of verifiable facts about a counterparty, right, then some of the details of like, well, what is their race, or things like that, like
Hmm.
like they may actually be immaterial to the kind of desire to make the transaction, right? And in a sense, those facts might end up being a hindrance to being fair to that counterparty, right? So
Exactly.
to me, in a kind of more idealized world, we actually have exceeding confidence in facts that we need, and then the facts that we don't need, we can just leave it to one side. We can just have it be like, well, those aren't factors, right? The factors that are relevant are the factors that we have, and those factors are proven. Like we have the mathematical proofs that we can drive these things to their final state. So that's very exciting. I'm very
Hmm.
excited to see big progress on testnet and mainnet on Lagrange. So
Thank you.
we're looking forward to this space. Just a final note as well. My fund, Gumi Cryptos Capital, is an investor in Lagrange, but as with always, do your own homework. The other facet of this is that I'm not bringing this to you because I want prices to go up. I'm bringing it to you because for the same reason I invested, which is that I'm genuinely excited about Ismael. I'm genuinely excited about this area and field of study and their incredible progress they're making. So thanks so much for joining the show.
Thank you, Miko. It was a pleasure being on the show.
Bye.
Miko